Hey everyone, this is Dr. Keith. Let's explore some relationships that aren't necessarily linear and see what options we have. So here we are in our chapter. Let's open the data file used at the beginning of this chapter right here, this bike buyers data set. Looks just like this. I'm on the numeric page. Once you've downloaded this, go ahead and open Tableau. I like how easy and quick to use Tableau is to learn this feature, and hopefully you've all learned it already in class by now. So here I have it open. I'm going to go to my data source. I've imported file. I added a connection by opening that Excel file I just downloaded, and I pulled the numeric worksheet here into Tableau. So hopefully you remember how to do that from previous chapters. But come in here to sheet 1, and let's go ahead and drop in age. Actually, I'm going to put in income first. Income is our Y. It's the variable we are predicting. And actually, let me select aggregate measures because this is more like what you're probably seeing right now. And then grab age and put it here on the x-axis. So typically we put the independent variable, the one explaining or causing the effect on the other variable. We'll put this in the x and the y on the y. So age determines income. That's how we interpret this. We've got one dot. That's because Tableau by default uses the sum function on measures, or numeric variables. So we're going to change that by going up here. Let's see. You may not be able to see that, unfortunately. I'm on a Mac. It makes it tough to see. So if you're on a PC, I want you to click on, up here you'll see Analysis. If you're on a Mac like me and you can't see this, just know that I've clicked on Tableau, and there's an Analysis option up above. It gives you this aggregate measures option. Deselect that. So rather than using the sum function, it just says let's show every single row or record and plot it according to the age and the income in that record. So when we look at this, it's tough when we have a lot of data to often tell exactly what the relationship is. Clearly it gets more condensed down into this corner, and then it sort of flares out this way and this way. The question is there a line that we can draw through this, like we've been learning in this chapter, a line of best fit that indicates the direction of the relationship? So come over here to Analytics, grab Trendline, and drop it first here on Linear. So let's not worry about these bars on either side for now. These are kind of like confidence intervals. But this line directly through it right here, this is our y equals mx plus b formatted line. So let's interpret this, the details you see here that pop up when I hover over it. So income equals 463.008 times age. So if you remember from algebra, the formula for plotting a line is y, and that's income. In this case, it's the dependent variable, equals mx plus b. M is the slope of the line. In this case, the slope is 463 times mx. X is the x variable, which is age. So and then plus b. B is the intercept. Meaning, where does this line cross the x-axis, the y-axis, when x is 0? So what this line says is that when people are born, when they're 0 years old, they're making $35,679.70 per year. Clearly, that's not accurate, right? With a linear, this line of best fit represents the sum of squared residuals from every data point, from here to here, from here to here. So this line is tilted at an angle to where if I take the difference between this point and the line and each point in the line, and I add that distance up, and I square those distances so I don't get any negative numbers from this minus this versus this one minus the line. So I square those, and the angle of the line that gives me the smallest sum of squared residuals, that's what determines this angle. So basically I take in any age and put it in that formula. So 30, let's take that age, put it right here. If I multiply 463.008 times 30 and add to that 35,000, that predicts the basically the average or the best fit, the best prediction of what someone's income would be at age 30. So if you do the math, let me do that on my phone here so I don't move that, so I don't have to move my cursor. That's 463.008 times 30 equals 13,890 plus 35,679.7. So the result I get is almost 50,000. So what we're saying here is that if we were to predict based on the data we have, our best prediction is that 30-year-olds are making $50,000 a year based on this data. So let's take a look at some of these other numbers. You see my p-value there of less than 0.0001. What that means is that the data, even though they look incredibly spread out, the data is close enough together that we can say with statistical significance that there is a valid relationship between age and income, meaning as people get older, yes, it's not just due to chance that their income goes up. There is something that's causing their income to go up as they get older. Now, clearly, it's not age itself that's causing them to make more money, but as people get older, they get more education, they get more experience, more knowledge, they're more likely to get higher paying jobs. So that's what the p-value means, though. It simply means that the relationship between these two variables is statistically significant and not due to chance. There is something about these variables. R squared. Now, we haven't quite gotten to this point in the chapter yet, but you'll learn it a little bit further down. R squared is a score between 0 and 1 that represents the percent of variance in the Y, the income, that is explained by age. So age only explains 2.86% of the variance in income. Now, that's not a lot, but it's enough that the p-value is below 0.05 and is statistically significant. So I would never discount or be disappointed in an R squared value that's really, really small, because again, harken back to our Netflix example. They paid $1 million for just a 0.01 improvement in R squared. The ability to explain and predict is still very valuable. But 2.86% is terrible, and I think we can do better than that. Well, in this context, sorry. I don't want to contradict myself, but it's not great in this context, and we can do better. Why? Well, clearly people don't make money between ages of 0 and very little money as you approach 20. They haven't graduated from college yet. So the line would be best, but we can't model that because we don't have anybody in our data set that's younger than, looks like about 24 or 25. So there's still other bumps that are going to happen. When people graduate from college, there's a spike. When they graduate from a graduate degree, there's a spike. When they retire, it maybe goes down a bit over time. There's a variety of factors that would explain this data, and clearly a straight line through it is not the best explanation, because we don't get more income simply because of a birthday. When we turn 1 year older, there's not a measurable amount of income added to our salary that is the same every year. That's what a straight line implies. It implies that every year the exact same amount of income is added each year so that we can model it with a straight line. But that's not the case. Click on this, drag it off. We have other options. Click on trendline, and look, we have logarithmic, exponential, and polynomial. So let's start with, before we even pick one, let's start with the theory. Theoretically speaking, should people make a lot more money at first and then it gets smaller and smaller over time? Or should they slowly start making a little bit of money and then it spikes or increases? Or is there a series of waves in it? That's what we're trying to decide. Well, let's just try all of them. So trendline, let's start with exponential, because I think this is the next worst one. So this gives us a line that curves a bit, and Tableau automatically picks the rate of increase, or the amount of curve that best represents the data for you. So if I hover over this line, you'll see our formula has now changed. Income, it's now taking the natural log of income, and instead of just income as it is. So it's saying that if you take 0.009 multiplied by age, add 10.3458 to that, that should equal the natural log of income. Well, look at our R squared. It's actually worse, 0.024. What does that tell us? Well, the p-value is still low, so that means this line still indicates that there is a statistically significant relationship between age and income, but a straight line does a better job of modeling this data than this curved line, which tells us that it doesn't curve up. It's much more likely to curve down, because our R squared results from the straight line were better than this. Now, again, well, hold on, let's take this off one thing at a time. Let's now take the trend line and drop it over logarithmic. So here's our logarithmic line, and here's our formula. Income, rather than taking the natural log of income it's going to take a log base. Actually, I'm not sure. I have to look that one up. I'm not sure what base they're using on that log, but Tableau automatically picks the one that it feels best represents the data. Again, the one that reduces the sum of squared residuals. Anyway, they're saying that 24,459.80 cents multiplied by the log of some base times age, plus add to that negative 35,729. Why is that negative? Well, look where this line goes. It crosses the x-axis before it crosses the y-axis, which means that when this eventually does cross the y-axis, it's going to cross it at negative 35,729.60 cents. But look at our r squared, 0.0404. So that's clearly better than our 0.028 and the 0.024. This logarithmic modification to our line is a better representation of what's actually going on with our data. So our data says that as people get older, they do make more money, but the rate of increase of that more money decreases. Well, this still isn't perfect, right? We're showing here that 10-year-olds are making $20,000 a year. That's not really great either. Let's pull that one off and drop on there a polynomial. All right, now we're getting somewhere. So a polynomial, let me show you the formula. This allows for multiple x variables and multiple slopes. So instead of having y income equals mx plus b, it's y equals m1x1 raised to the third plus m1x1 raised to the second plus m1x1 minus the intercept. So it can add as many x variables as it wants to reflect the number of curves. So we have 3 inflection points. It inflects here, here, and here, which is why we need 3 variables. The regular x variable, an x squared, and an x to the third. If it inflected again, we would need an x to the fourth. But it says, Tableau automatically checks that and says, no, your data doesn't show that you need that. It's better to use this formula with 3 variables. And look at what our r squared has done. We're now up to 8.56%. So that's much better than our straight line was at the beginning. Anyway, these are things we can test for and include in our predictions. Tools like Tableau make it really easy.